decided to talk about entropy and order. So what you have heard, in the previous talk, I mean, the overwhelming idea is that the entropy is disorder. So the entropy of the universe always increases. That gives us a direction of time, and so we are going towards more disorder. That's true, okay? But it does not deny us having an ordered state. And how, that's what I'm going to just explain here. Considering a simple model system, the reason that it does not deny us having an ordered system is that this increase of entropy of the universe is somewhat a weaker condition. Okay, it does not tell you that everywhere the entropy has to increase. It can increase, in any spontaneous process, it should increase, overall entropy of the universe should increase. And that basically leaves room for having systems with lesser entropy states. And that also happens, in equilibrium, where equilibrium we basically define is to be a state we arrive at by increasing the entropy. Now, what is a system? So when I'm going to talk about these things, so I would be basically considering a system and its environment. What is a system? A system is something, we basically measure things on. We know, different quantities about that. And what is the environment? Environment is, the other part that we do not know much about, unless we put some kind of condition under which we get to know some properties of that other part. So that basically we would be calling the environment. And let me define here entropy as a function of probability distribution of the system. So I told you that we know things about the system. So we know the probability distribution of states of a system. What this particular system we're going to consider, I will come to that later. So given a probability distribution of a system, the entropy is defined by this function. The entropy is basically average of this log pi. Okay? I is a state of the system. There can be 10 states, 20 states, 100 states of a system. And if you want to find out what is the average of this log pi, pi is the probability, then this quantity is a measure of the entropy. So there are two things. One is the system we know things about, and we have a measure of the entropy. There is this environment we do not know much about, and you cannot have a measure of entropy there. So that is where basically second law rescues you. We'll come to that later. So it has a few desirable properties. So the thing that we have been talking about is this maximization of entropy, that determining everything, right? So if the entropy has to be maximized, then this function must have a desirable property that it has an upper bound. I mean, this is a positive definite function. If you just consider that this is normalized, so this is negative, so that negative sign goes away. So, I mean, this is less than 1, so that makes it negative. So this is a positive definite function. And since we would be using its property that a system we are going to define to be in equilibrium corresponding to a maximum of this function, so it must have a well-defined maximum. Another property I have just forgot to write it down here is that, I mean, it's extensive. It's extensive means basically if you increase the number of particles in the system or mass, then the entropy increases proportionately with that, with the number of particles in the system. Okay, given that, let us consider a system of these 10 spins. Okay, these spins, this is such a system, let me define it this way. When spins are up, they have energy minus epsilon. And when the spins are down, a spin has energy plus epsilon. So up is a lower energy state and down is a higher energy state. Okay? So in this state, this state is a macro state of the system. So let me define a macro state of a system is defined by the macroscopic property of the system, say the energy of the system. So this is a macrostate of the system which has an energy minus 10 E, right? Now if I flip 5 spins here out of these 10 spins, so this is a system which is another macrostate which has energy 0 because 5 up and 5 down, okay? Now this is a macrostate which has only one microstate in it. That is, in only one possible way, this macrostate you can get. But this is a macrostate you can get in many different ways. Most probably it is 252 different ways, because you can just, permute these up and down spins in here, right? If you do that, that's not going to change your total energy of the system. That would always remain 0. But you would be getting this state with different spin configurations, okay? So what is the entropy of this thing by the definition I have shown to you? So for this macrostate, which I call ferromagnet, this is 0, right? Log 1 gives you a 0. For this state, this paramagnetic phase where the energy I'm considering, so there is a problem. I mean, normally this ferromagnet, paramagnet we define in terms of magnetization, but I'm doing here that in terms of energy, in any quantity you do. Okay, if it is such that out of all those 252 states, only one state is possible and has a probability unity and all others have probability 0, then its entropy is again 0 by the same formula. So if there are 2 states and those are probable and all other 250 states are having probability 0 to appear, then it would be having, you would be having an entropy log 2, okay? So if all the states are equally probable, that is this paramagnetic phase you can get in, in all the microstates with equal probability, then you are going to get, this entropy to be maximum. This is this. So that tells you when there are more options, and it's obviously difficult to know by, once probing the system about all of them. That is the system, that is where we call the system is in kind of disorder. So entropy here basically shows you that it's a measure of that kind of a disorder. So entropy basically is a measure of the degeneracy of a state. So a degeneracy basically corresponds to the symmetry of the system. If the system has more symmetry, then it's more degenerate. Okay, there would be many states you would be seeing which are corresponding to a macro state. Anyway, so let me go to the microcanonical ensemble from our definition of entropy. In the previous slide, we had seen that when there were, in the paramagnetic phase, 252 states and all states were equally probable, then the entropy was maximum. And if I call that 252 number to be m, then this entropy basically becomes S micro, that is entropy of the microcanonical ensemble, to be log m. In the Boltzmann formula, you see here a k outside there. That's because in physics, entropy was defined as a quantity with a dimension, energy per temperature. So that requires a dimension fixing constant that which could be fixed to 1. But anyway, that does not matter much. That Kb does not matter much. But this is your entropy formula for the microcanonical ensemble. A microcanonical ensemble by definition is something where a system is isolated from everywhere, so it does not have an environment. Given that there are quantities which would remain constant forever, like the energy of the system, because there is no exchange of energy with the environment, like the number of particles of the system. So those things would remain constant, okay? And those constant quantities would basically define the macro state of the system, which is only one macro state. And entropy corresponds to basically the microstates under that macro state. There is no reason that you can differentiate between those microstates. So that tells you the entropy of all those states should, the probability of appearing in all those states for the system would be the same, and that basically gives you your maximum entropy, that is S micro is basically log m, where m is the number of microstates. If I consider, okay, let me go to the second one. I'll come to that. Okay. So now let me consider a canonical ensemble. A canonical ensemble is a system where the system is surrounded by some kind of an environment, right? And what does that environment do to the system? That it fixes something of the system because of the interaction of the system with the environment. So let us think of that there exists some kind of a quantity which is a function. This xi basically is telling you which macro state the system is in. The previous example that I had shown you, the spin thing, there were actually 11 macro states, all up to all down, right? There were 11 macro states. Now, if those 11 microstates, as I had told you, are characterized by their energies, that energy you can consider to be this xi. So this h is a function of the quantity that characterizes that macro state, and h basically has its average defined due to interaction with the environment. In whatever way, due to interaction with the environment, its average is defined and the system has to be there. That's the condition. I mean, the system has to follow this thing. So if that is the case, then the entropy of the system you can write like this. This formula I have shown you previously. And this is basically 0. The moment the average is defined like that, this is 0. This is the constraint. So you just bring that in, multiply by Lagrange multiplier into the definition of entropy. It's not changing the entropy, right? Then you maximize the entropy, take derivative. You get this thing. From that, you have got this expression. Okay? So you see that. What is a microcanonical ensemble? A microcanonical ensemble is something which exchanges heat with the environment. As it exchanges heat with the environment, I mean, it reaches its equilibrium through that process. Reaching the equilibrium means that there is no average heat transfer between the environment and the system. So if there is no average heat transfer between the environment and the system, then the constraint is that the average energy of the system is constant. That is this constraint. So interaction with the environment has set a constraint here, and that through maximization of the entropy gives you this kind of an expression. If you consider a grand canonical ensemble where the system and the environment can exchange particles, so there you would be having another constraint here, considering that particle fluctuations, and that would give you here a mu beta n term. That would be your grand canonical distribution function. But this is something where I'm considering these macro states to be non-degenerate. I'm considering that to each macro state, there is only one microstate, not many microstates. I have not taken into account so far that microstate thing here. Now, let me consider degenerate macrostates. So the previous problem, as I had shown to you, I mean, this ferromagnetic phase where all the spins are up, there was only one microstate, and where there were 5 spins up and 5 spins down, there were 252 microstates. I'm now going to consider this kind of a situation. Previously, I considered only 11 macrostates. Now I'm looking at the substructure of those macrostates. Now, what has been the principle to come to a probability distribution? That was maximization of the entropy. I'm going to follow the same thing. Now, if I consider this paramagnetic phase where the energy was 0 but had 252 microstates, there is nothing that can differentiate between those 252 microstates because it's giving me the same macrostate. So they are all equally probable. So if they are all equally probable, then the corresponding entropy, the way I had written it, now I have here introduced this Kb explicitly. So corresponding entropy of that my ith microstate is basically this thing. So the number of microstates is coming to be e to the power Si over Kb, right? So that's again based on maximization of the entropy. Of the structures, those are hidden inside a macrostate. You are maximizing the entropy there. Now, obviously, the probability of observing a macrostate now which has degeneracy would be the probability that I have found out previously times its degeneracy. In how many ways I can get to that state. And you can now put here in the place of this entropy maximization condition, and you get this thing. This is the expression. Now it shows you that there exists a quantity which is, like for the macrostate, this is what we call Helmholtz free energy. But when this quantity is minimum, the probability of that state is maximum. Okay, when this quantity is minimum, probability for the system to be in that state is maximum. Now this quantity is nothing but this quantity, right? EI over KBT minus SI over KB. So when this quantity is minimum, then the probability for the system to be in that state is maximum. So that tells you, that basically shows you that even by all maximization of entropy, you can have ordered state, and that is in this way. So the energy states, macrostates of the system that I have talked about are basically this minus 10 E epsilon to 10 epsilon, right? Now, this is the thing that has to be minimum for the probability of a state to be maximum, right? Now, for the paramagnetic state, the energy was 0. So this EI part is 0. This one was, SI was maximum, log 252. So you have got this quantity, particular quantity is of this value. Ferromagnetic phase, this quantity you can calculate, there is no entropy, only the energy part is there, is this much. So the ferromagnetic state, the ordered state, when this thing is less than that, then this ferromagnetic state would show up, although it does not show you apparently that entropy has been maximized. But the whole procedure we followed, that was based on maximization of entropy, right? So that gives you a temperature as you compare this thing. If you go below this temperature, then your system would actually prefer to go into a ferromagnetic state, an ordered state. And if the temperature is above that, the system would actually like to go to a disordered state where there is more entropy. So then we are at a problem. I mean, we have talked about maximization of entropy so far. Now I'm seeing I'm going to get a state, following that way, I'm going to get a state of my system which is ordered. And apparently I'm just decreasing disorder. How can that happen? So that is where comes your second law. And that tells you what you have been so far considering is not the entropy of your system alone. You have been considering the entropy of the system and the environment. Okay? Entropy of the system you can measure. Entropy of the system you can measure because you know the probability distribution of your system. When the system has reached some kind of a stationary state, that if you measure the probability won't be a function of time. That is something we call equilibrium, comes by maximization of the entropy of the universe. But there is a problem. The problem is that the entropy of the system I can measure, the entropy of universe I have no idea about, right? Because entropy of the universe or the environment, this environment is something whose I only know the intrinsic parameters, like temperature, pressure. I do not know any extrinsic parameter. Entropy itself is an extrinsic quantity. That is, I had told you, I mean, it increases with the mass of the system, number of particles of the system. Like if you have a thermometer holding, if I hold a thermometer here, I mean, it would show some kind of a reading of temperature. So the thermometer has come in equilibrium with this room thermally, and that shows me what's the temperature of this room. Because when it comes to equilibrium, that intrinsic property is the same of the system and the environment. If I hold some gas here in some flexible like balloon Arnav showed, and it's not expanding, neither contracting, in that situation it means that the pressure of this gas inside this balloon is the same as that of the outside. So that's again an intensive quantity of the environment that you know by observing your system, but none of the extensive properties you know of your system. Okay? And you require there a principle to handle this entropy thing, and that your second law gives, basically Clausius theorem gives you this thing, that entropy increases in any spontaneous process or any irreversible process, and it's equal to this delta Q by T when the process is reversible. Okay? So normally it requires your system to, I mean the process to happen very slowly. I'm not going into the details, maybe if time permits later on. So this relation basically rescues you. It shows you that the entropy of the system and the universe is actually increasing even when the system goes to an ordered state. How does that happen? So now consider the system I had shown to you, that spin system, and say the spin system was in equilibrium with the environment at a temperature T. And that dictated an average energy of the system, as we have seen this thing in the calculation for the in the canonical case. So when your system is in equilibrium with the environment, depending upon what kind of interaction it's going through with the environment, a constraint would come on that, and that constraint here is basically this, its energy is, average energy is this, or energy basically is this. Now you suddenly change the temperature of the environment, consider this to be a virtual process, from this T to this small t, where this is smaller. This small t is smaller than the big T. Here I'm talking of a process, I'm not going into the details of that, later I will come to that, that you have suddenly changed the temperature of the surrounding to a lower value. What has gone into it, I will come to later. Now as this thing has happened, the system would not immediately respond to that, but it would take some time to respond to that. So when you did that just momentarily, the system is in its equilibrium state that previously it was in, and then slowly its temperature would fall, and the energy would decrease, and come to another average energy, this small e, and the temperature, this small t, when it comes in equilibrium with this condition that the environment temperature is small t. And so you have reached from this equilibrium to this equilibrium. Now consider a non-equilibrium transient state in the middle. So this tau is a temperature which is basically greater than this T because the system is moving from here to there, but this is smaller than this T. Whatever, at this stage, if dq heat is transferred from the system to the environment, system is losing energy, right? Because it has to move from a higher energy state to a lower energy state. You have suddenly reduced the temperature of the environment. We have seen in the previous case that if you reduce the temperature of the environment, okay. Here comes a problem of mind considering that to be macrostate defining as an energy state, not a magnetization state. But no, it's not, because I had put a minus sign there. Because your ordered state was a minus epsilon, right? Minus 10 epsilon. So that means the low temperature phase, which was your ordered phase, that was the low energy phase, right? So as the system moves from here, this is a high energy phase, maybe the paramagnetic phase, and this is the low energy phase, the ferromagnetic phase, okay? So here, the system loses some energy, gives that to the environment, and that basically corresponds to, say, this heat delta Q. This delta Q by tau, which is the loss of the entropy of this system. If I consider this process to be reversible, not necessarily it has to be reversible, because it's normally is irreversible. So then this is the entropy loss of the system, and this is the entropy gain of the system. You see the gain, because this T is always, smaller than this tau, this gain is always bigger than this loss. So your entropy gain of the universe or the surrounding, that is more than the loss of the entropy loss of the system. Now that, by considering this to be a reversible process, if you consider that irreversibility, that is delta S is greater than equal to dq by T, you would see that we are always overestimating the loss. So loss is actually a little less than what we are estimating here. And we are underestimating the gain. So gain is always a little bigger than that. So it does not disturb you, because the system not necessarily would go through a reversible process from one state to the other as you have suddenly changed the condition. Now as you have suddenly changed the condition, that is a spontaneous process of your environment, okay, because your system has not responded to the environment yet. Now second law tells you in all spontaneous process, the entropy would increase, okay. So there is no decreases part coming in there. You had two increased parts, one decreased part, one loss, two gains, and we have shown at least one gain is more than the loss. So entropy of the universe is always increasing. Even a part of the system is being ordered. Okay? So that's the thing I wanted to show to you, that, I mean, it's the entropy of the universe or entropy of the whole system that you have to take into account to understand change of your system, I mean change of states in your system under varied conditions. Okay, there are many other things, but I think I have spent all of my time. Thank you.